Good morning, good afternoon, everyone. Thank you very much for joining our webinar today. I'm very delighted to have you all on board. My name is Richard Cluth. I'm the Managing Director with Bandweaver Technology. Also on the panel today, we have Mark Horton, Vice President with Bandweaver, and Sarah Phillips, who heads up the marketing. They will be helping and supporting me during the call. The format of the webinar is I will go through the presentation. Please, at any time, do feel free to submit questions. There's a button for submitting questions, and then we will address those questions at the end. So don't worry, you will have a chance to ask anything. Hopefully, I'll try and cover as clearly and concisely as we go on. The subject of today's webinar is fire detection for buildings and industrial facilities, and talking about the advanced capabilities of fibre optic linear heat detections. So the objectives of the webinar today, firstly, to introduce the principles of fibre optic linear heat detection technology, to demonstrate the benefits of the fibre optic sensors, and we'll go through a lot of the details, but the sort of key two are that you get coverage at all points along the assets. That's a robust and reliable technology with a very low cost of ownership. We'll show the enhanced performance of these systems, and some of the key factors are rapid detection, low levels of false alarms. And we'll show Bandweaver experience, so showing that the FireLaser linear heat detection system is the highest performance system available, and go through some of the extensive experience in fibre optic linear heat detection applications that Bandweaver has. And so the order I'll do that, I'll start off with a history of fibre optic linear heat detection, give an overview of what is a fibre optic LHD system, what are some of the advantages of these systems, and then we'll go through some real life installation examples to give some colour to that. And finally finish off with just a few details about Bandweaver. So the history of fibre optic linear heat detection systems. These have been around since mid-80s, 1986, and initially they were used in road and rail tunnels primarily. Since then, more than 30,000 systems have been installed worldwide. And it's become a very mature technology. And so as it's matured, the economies of scales have improved, the prices have lowered, reliability improved, usability improved, meaning this technology is expanded to a number of other areas. And if we look at the example of how fibre optic linear heat detection expanded within the rail network, it gives us an insight as to how this technology evolved. As we said in the previous slide, the technology started in the tunnels, and the longer lengths made it economically attractive. But as it's a very flexible system architecture, there's no, cables are very simple to install, no in-field power or comms required. The fibre optic linear heat detection expanded to many other areas. So escalators, station and platform concourses, facilities, building, and electrical assets. And as we've seen, the application spread from the rail network to these buildings, generally there's some common factors that came into play that makes this technology attractive. So complete coverage, if the user requires complete coverage, no gaps between sensing points. If there's a large area, so large numbers of sensing points, it works well. Areas difficult to test and maintain, so whether that's confined areas, difficult to reach areas, or challenging environments such as high humidity, dust or other particulates or explosive atmospheres. If this is one of the sort of factors that come into play, then this technology certainly started to expand into those areas. And we saw, as well as expanding within the rail network, it expanded to numerous other areas as well. And so what we'll be focusing for this presentation is building in industrial facilities. So we'll look at examples of warehouses, hangars, manufacturing facilities, car parks, cables, trays, ceiling voids. We'll look at all of those in this presentation. It also goes into many other applications: freezers, furnaces, abattoirs, other high humidity environments, historic and other specialist buildings. In the interest of time, we won't do those in this webinar, but we certainly can do that on future webinars in request. So first of all, an overview of the technology, what's behind it. So the technology behind the fibre optic linear heat detection is known as distributed temperature sensing, or DTS. The key to this technology is the system operates using standard telecoms fibres and no specific sensors are required. The system uses OTDR technology, which stands for optical time domain reflectometry, which is a bit of a mouthful, but it's very similar to the radar time of flight principle that we'll go through the next slide. But the key takeaway is that the fibre is the sensor. No point sensors are required, so you don't need to worry about where you position the sensors. So here we'll look at the basic principle of the fibre optic linear heat detection system. A system's essentially very simple. It consists of a controller unit and a sensing cable, which is based on just standard fibre optic cable. The controller sends a laser pulse into the fibre. The laser pulse interacts with the fibre, and some light is reflected back to the controller. The time it takes for the reflected light to return gives the precise location, which is why it's very similar in principle to radar, the time of flight. And the controller, by analysing the power and frequency of the reflected pulse, is able to determine precise information on the temperature at all points along the fibre. Depending on the sampling frequency and range of the system, the measurement points it divides it into vary from 50 centimetres to 2 centimetres. For most fire detection applications, it's 1 metre, which means you get a measurement every 1 metre along the cable. If we then install the sensing cable into a building, we can provide complete coverage of the building. And this has a number of benefits. First, that there's no gaps in coverage. And secondly, it makes planning and installation very simple. You don't have to worry about where you're putting the individual sensing points. And just to emphasize that point of complete coverage, we'll look at an example of a continuous fiber optic linear heat detection system, the Bandweaver FireLaser, versus a multi-point line type system. And these have multiple points. They can have more than 200 per unit. But on long lengths, these end up getting spaced out where they can be 10 meters apart or even more than that. So if we look at the fiber optic linear heat detection system, we see that if you have a small fire event, you will detect it directly above the fire, which means you can react very quickly to the fire. And wherever the location of the fire is, you detect directly above it. So you see wherever we move it, it detects it. With the multi-point, the fire is, the likelihood is that it's not below a sensor and it's between them, and it can be up to 5 meters away. So you would detect it much later. The fire would have to get much bigger to be detected by either of these points. Similarly, if it's here, sometimes it will be below, but more often than not, it won't be. So the continuous linear fiber optic linear heat detection system is a much more robust form of coverage. And let's have a look at one of the units. This is what the FireLaser looks like. So start with the controller, which is the heart of the system. It's a very compact unit, which is completely self-sufficient and completely configured and programmed through this touchscreen LCD. It has channel indicators showing which optical channel is active. It has other indicators showing if there's an alarm, a system fault, the laser power is on or the system power is on. It has a lockable access panel with additional features, but this is only available to people with the authorized personnel. Just to say, so you can have up to 4 channels per unit, 10 kilometers in range. So a unit like this can measure up to 40,000 sensing points. If we look at the back panel, we can see those are the 4 optical connectors. These are simple push connectors known as E2000. We have the Ethernet and serial ports for the Modbus connectivity, the relay connectors for interface with the fire control panel, and the power supply, 24-volt DC, often supplied through the fire control panel. For the sensing cable, as we mentioned, this is based on standard telecoms fiber optic. The fibre optic is completely passive, has no moving parts, and is not susceptible to corrosion. So this cable can last more than 30 years. And in fact, many of the original telecoms cables installed in the 1970s are still working 50 years later. Other benefits of the fibre optic cable is that it's immune to electromagnetic interference, does not require any in-field power or communications, which again increases reliability and reduces installation costs. They're lightweight and flexible. Typically, they're in the region of 3 to 5 millimeters diameter. And this provides a lightweight, flexible cable, which is easy to install, but provides sufficient protection for the rigorous installation and the lifetime of the cable. And you can see two examples here, one with an inner metal tube and an outer metal braiding, and then one with no metal that may be used in an area of higher electromagnetic activity where there's potential concerns about conduction along the cable. With regards to system integration, the system integrates in two key ways. Firstly, and simply relay to the fire alarm control panel. Each of the alarms can be signed electrical relay, and so in the event of alarm, that relay is triggered. The second method is send information via Modbus over TCP/IP. This is typically to the SCADA or building management system, and Modbus contains more detailed information, including the precise temperature and the location. So in addition to basic triggering of fire alarms, other systems can be activated accordingly. So we'll move on to the talking about the advantages of some of these systems. And we're talking about the advantages. We'll split it into two areas, the physical and the information advantages. So talking about the physical, you can have reduced infrastructure. It's a very simple single cable to install, so it's lower than other in technologies. Very robust, resistant to electromagnetic interference, intrinsically safe, corrosion free with no apertures, joints or moving parts. It's resilient to cable damage, so you have uninterrupted detection even if the cable is damaged. Moving on to the information benefits, you have location accuracy. As we said, that the system can identify to within 50 centimeters. Early detection. With this complete coverage and smart alarms, we can detect much earlier than conventional systems. And this earlier detection and location accuracy allows the user to make much more informed decisions and lower their overall risk profile. So as I talk through the advantages, I'll start off talking about the redundancy. This technology has some unique redundancy situations. We'll go into the smart alarms and zones, and then talk about maintenance and reliability and the benefits of the low cost of ownership and low levels of false alarms of this technology. So starting with redundancy, so there's two levels of redundancy. We have a controller redundancy, so continuous in operation in the event of a controller failure, and cable redundancy, so continuous operation in the event of cable damage. And we'll show how this works for single and multi-facility configurations, and that you get economies scales the larger facility you use this technology in. We'll start with the simplest though, a single system with a loop configuration. This is a single cable. This is showing the two fiber cores, but if you look on the right, this is the configuration of the cable. So it's a single structure, but with a green and a red fiber. So for the ease of showing the principle, we're showing the red fiber coming out of this channel of the FireLaser and the green fiber coming out of this channel. So during normal operation, you'll see the red channel sends the laser pulse around the red fiber and the green around the green fiber, and it takes it alternatively. And you can see you have complete coverage around the facility wherever the cable is installed. In the event of a damage to the cable, you'll see the red pulse and the green pulse now can only go as far as the point of damage, but because it's a loop configuration, it can approach it from each side. And so you still have full coverage even in the event of cable damage. If we go to the next level of redundancy, it's adding a second controller in. So here we're looking at controllers 1 and 2. Again, a single cable configuration, but with two cores, the red core coming from controller 1, the green core coming from controller 2. So during normal operation, you will see the green pulses coming from system 2, the red from system 1, complete coverage at all points along the asset. If we take system 2 out of commission, we still have system 1 providing full coverage. And conversely, if we take system 1 out, the green fibre from number 2 provides complete coverage. So fairly standard, I guess, with normal redundancy, that if one system goes down, the other takes over. Where this technology, comes into, has an extra dimension, is that you also have the cable cut in this scenario as well. So if you have cable damage, you'll get full coverage. So either in this scenario, either a controller goes out or a cable cut, you have full coverage. So very robust. And this scales up very nicely as you move to more assets and more units. So if we look at an example here where we have 6 facilities, this can be covered with the full cable and controller redundancy using 4 systems and with 2 core cables. So it's a bit complicated, the fibre optic path here, but the same happens. If any controller or any cable goes out, you still get full coverage. And this is showing car parks in this example. So it could be multi-stories of a large car park. It could be multiple buildings within a complex, multiple tanks. There's many different scenarios that this can work. Moving on to smart alarms, which is one of the most significant advantages for this technology. And in the next few slides, we'll explain the principle of both, and we'll go through some worked examples. But the sort of key advantages are you can detect earlier than with conventional technology. You can reduce the number of false alarms by precisely configuring to each installation. You can customize each zone to the specific environmental conditions of that zone. And finally, with the improved information flow, you can greatly expand the options for system integration and maximizing the value of the data. So let's look at the 3 different smart alarms you can have. So absolute temperature, this is the value above which the alarm will trigger. This could be fully configurable, can be set at any value the user requires. So typically for most industrial applications, this is set at around 58 degrees C. And this is very different from conventional copper-based linear heat detection, which has a set point, but that set point is defined by the physical configuration of that cable. So if basically when it melts and the conductors come in, so it's not changeable once you have the cable in there. We then have rate of rise, which corresponds to how quickly the temperature rises within a defined time frame, which is typically a minute. One of the key advantages of rate of rise is it can detect much earlier than for absolute values. So typically this is set at around 9 or 10 degrees in a number of applications. If you have an ambient temperature of 20 degrees, for example, you would have the system trigger an alarm at around 29 degrees, which is clearly much lower than the 58 degrees C absolute level. So much earlier detection. And finally, the temperature deviation or differential alarm. This triggers when there's a temperature peak, which within a zone that deviates from the average value. Again, this can trigger much earlier than the absolute value, but also can trigger when rate of rise may not. If you have a small fire, which is too slow to trigger the rate of rise, this can be a very powerful addition to the smart alarm portfolio. This leads us into smart zones. The smart zones are software configurable and can be set to the user's precise requirements. Up to 1,000 zones can be defined, and you can see a screenshot here that shows the very intuitive nature of these. So you can name the zone whatever you want, assign the optical channel, which of the relays will trigger in the event of alarm, where does the zone start, where does it finish, and then which alarms are applicable in that zone. And you can choose one or you can choose multiple. You can have, additionally, you can have overlapping zones. So you have ultimate flexibility with the smart zones. And to give an example of that, let's look at the comparison of a fiber optic linear heat detection system with a conventional copper-based linear heat detection system and a multi-point line size sensor. So let's look at the functionality. So in this scenario here where they're all installed, the fiber optic linear heat detection system, the conventional, would offer complete continuous coverage. There's no gaps in the measurement. The line point, as we said, the sensors may be up to 10 meters apart. The fiber optic linear heat detection and the multi-point are measuring temperature at all points. The conventional does not measure temperature. it has physical parameters, i.e. it melts when you exceed the alarm temperature. So you can configure the fiber optic and the multipoint. You can't configure the conventional. Equally, because you're measuring temperature, you can set the rate of rise for the fiber optic and the multipoint, and you can have the deviation for the fiber optic and the multipoint. So if we look at that within a tunnel environment, we'll look at an environment where it's a fairly small fire. So it's starting out. There's also wind, so it's blowing the fire down the tunnel. This means that the hottest point is not at the roof of the tunnel, and the hottest point is not at above the fire. It's actually further down in the section 4. So if we look at how the temperature evolves at each of these points, you can see in each of the zones 1, 2, 3, and 4. In none of these zones does the temperature at ceiling level with the cables installed become close to triggering the absolute value of 58 degrees. If we look at the rate of rise and the deviation, the picture gets a bit more complex, but you can see the rate of rise only triggers in zone 4 where there's enough of a rise, and the deviation triggers in zone 2 and 3 and 4, but none of them trigger in zone 1. So what we see is within this environment, the only system to trigger in the zones would be the fiber optic linear heat detection, which will trigger in zones 2, 3, and 4. The others will not. So it shows how it's a very robust technology, and how the early detection and the continuous measurement coverage means you can detect much more early and comprehensively than other systems. And detecting early is very important. You want to detect before damage extends, before there's, for example, flashover in a car park, where the local fire suppression system can be effective and put out the fire and not have to have fire department intervention. So we'll have a look at a 4-channel system to show how the rate of rise measurement works, because it's very important, because it's across a number of measurements. So when we look at a 4-channel system, only one sensing cable is active at any one point. So you can see here, it's rotating through the different fibers. And it's important to cycle through as quickly as possible, because rate of rise, you need 2 cycles. So if we watch this cycling round these cables here, and we have a fire event here. This fire happened since the last cycle, so it hasn't been measured yet. So now the system measures on this fibre. We get the first temperature measurement. It's too low for absolute value, so the alarm is not triggered yet. As it comes round for the second measurement, we get the second measurement, and there that gives you an idea of how the system works. You need 2 measurements for the rate of rise. If we have a 5-second measurement per scan, we have 4 channels, we have the 2 cycles for the rate of rise. This means it's 40 seconds between for you to alarm. And this is reasonable in most scenarios, but you wouldn't want to go much longer than that. So the FireLaser system by Bandweaver measurement time is 5 seconds. Some of our competitors go as high as 30 seconds, which means they cannot use multi-channel systems. Spatial resolution is also very important. Some fiber optic linear heat detection systems have to increase spatial resolution at longer distances. So it can go to as much as 4 meters at distances greater than 7 kilometers. The Bandweaver FireLaser resolution is 1 meter across all distances, so even at 10 kilometers. And when we say measurement, this means it takes a measurement every 1 meter. So you can see this is what a 1 meter measurement looks like. This is what it looks like when it's 4 measurements. And finer spatial resolution means shorter detection time and lower risk. And again, we'll work through an example to show that. So if we have an example of a fire here, where the plume of the fire is 4 meters at ceiling height, this is a relatively small fire, so the hottest temperature here is 100 degrees C, but at the extremes of the 4 meters, it's as low as 30 degrees C. We'll see with a 4 meter spatial resolution, you're actually measuring 56 degrees C. With a 1 meter spatial resolution, you're measuring at the 100 degrees C. So you're measuring the hottest point and you're detecting 100 degrees C. So we'll show how how that works in an alarming environment. So if we look at this top example here, we have the Bandweaver FireLaser system with a 1 meter spatial resolution. So you're getting 1 meter along the length. There's initial temperature of 25 degrees C, alarm set to 60 degrees C. The other system, 4 meter spatial resolution, so you can see it's broader, also starting at 25 degrees C. And as the fire evolves, we'll see how the temperature that the systems is measuring goes up, but goes up at different rates based on the spatial resolution. So as the smoke starts to come in, you'll see the temperature rising. Here it's up to 40, here it's 35. As the flame spreads, we get and you can see as it evolves at the end, the system here is measuring the 100 degrees C, here 56 degrees C, and it still hasn't alarmed. So you can see the power of the finer spatial resolution. And the FireLaser is the highest performance system by Bandweaver. So we have 5 seconds response time for distances to 10 kilometers. This is up to 6 times faster than competing systems. 4 times finer spatial resolution, so the 1 meter versus 4. Only the FireLaser can operate with 4 channels at longer distances, which means we guarantee maximum 40 seconds between rate of rise measurements. And here's some of the parameters that are used for the EM5422 A1N rating, and these are publicly available. So you can see the Bandweaver 10 kilometer, provider B 8 kilometer, Bandweaver measurement time 5 seconds, provider B 30 seconds, Bandweaver spatial resolution 1 meter, provider B 4 meters, number of channels 4, provider 1. So clear advantages. And if we're comparing to other technologies, the main technologies, we normally compare against are, smoke and heat detectors. So smoke detectors, point detectors, optical beam and aspirating detectors. For the heat, it's against point detectors, all the linear systems we've seen, the copper-based, multi-point and the fiber optic. So common issues with smoke detectors. So with the optical beam detectors, they often physically get blocked. This can be overstacking of shelves in a warehouse scenario. It can be by dust particles, which can either cause false alarms, or the dust can coast the lens and reduce sensitivity. Or in the case of aspirating detectors, again, false alarms or aspiration vents blocked. The fiber optic has no apertures, no moving parts, so it's not affected by any of these factors. Similarly, if we look at the standard sort of maintenance issues with some of these connectors, so cleaning and removing dust and other particulates is not something that we need to worry about. When there's painting or construction work, existing sensors have to be covered. Often they're forgotten to be uncovered afterwards. And if the construction or painting work is over extended period, you need a backup fire detection system while these are covered. You have battery management replacement, regular inspection, cleaning, lensing and ports, and realignment of detectors, none of which is an issue for the fiber optic linear heat detection. Similarly, for testing of devices, in some cases, it can be very difficult to get into confined spaces. You've got multiple units you need to test, or you need to get up at ceiling level, and it can be quite a difficult task. With the fiber optic linear heat detection, as we said, you have measurements all along the length, so you can bring your test port down to a convenient level where you can test at ground level. And so, we've talked about the different aspects, and so it's very important when you're looking at projects to look at the whole life costing. So if we said at the design stage, with this technology, you don't need to worry about how to position each sensor, so you have lower design costs. Procurement, it's a simple controller and cable, it's a simpler procurement process. Installation, single cable, no in-field power or comms, makes it much easier. Simple annual test, again, a single cable. Almost no maintenance for the cable, so you don't have any maintenance upgrade costs. We've shown it's very robust architecture with the redundancy, so much less downtime. And the capital costs, you have great economies of scale as you move to large numbers of points. So we're seeing that when increasingly as customers are doing whole life costing exercises, the benefits become even more apparent, and they're more and more turning towards this. You also have the softer costs, the public image. we'll show in some of the projects going forward that using high technology is attractive. Similarly, sustainability, eco-friendliness. This has no low power, no battery. It's very environmentally friendly. And from a health and safety perspective, it's intrinsically safe, fast response, so it protects your reputation as well. I've put in this table to give a summary of some of the benefits versus the other technologies. I won't go through this now, there's too much to go through now, but for anyone who wants a copy of the presentation, you can have it afterwards and you'll have this as a reference table. So we'll now move on to some real life installations that Bandweaver has participated in. We'll look at a textile factory in Turkey, a refinery warehouse in China, a car park in the Netherlands, a sealing void in Singapore, and then Istanbul airport. So we'll use examples from around the world. We'll start with the textile factory. This is done with our partners BTS Yangin in Turkey. I believe Levent is on the call today. It's his birthday today, so happy birthday to you, Levent. This factory for this site, the owner was looking for a reliable technology to deploy across multiple sites. Each site is 200,000 square meters, so fairly good size. A textile factory, there's lots of particles in the atmosphere. It's a very challenging environment. The owner previously used point smoke detectors, and these failed due to blockage because of the particles in the air. So the customer was trialing different technologies. They looked at a number of different technologies. They carried out a proof of concept on a small scale, starting with aspirating smoke detectors. This didn't work, the pipes got blocked. Also, when they scaled it up, look at the whole life costs, it worked out to be too different league of costs than the other technologies. Optical beam detector, the lenses became dirty, the beam less energy, it lost sensitivity, so this didn't work. The copper-based linear heat, because it didn't have the smart alarm functionality, it detected much higher, and they wanted a faster, earlier detection than was possible with the copper-based linear heat. So the fiber optic linear heat detection was detected and deployed successfully. It was deployed at ceiling level. The ceiling height was between 8 to 11 meters. The spacing between the lines was 8 to 9 meters. In this facility, 4,600 meters of cable was deployed in the factory, both in the production and the warehouse areas. The system used the smart alarms, rate of rise, deviation, two-channel loop configuration with redundancy. The owner liked it a lot, so then successfully deployed to 5 sites. So this is currently now protecting more than 1 million square meters with 5 systems. Moving on to refinery warehouse Sinochem in China. This was a $5 billion petrochemical refinery facility. It was very much focused on advanced technology, resource efficiency, sustainable development. So those were factors they looked into when they chose the fire detection systems. It's a large site, 2.7 million square meters, 12 million tons annual capacity. So in the storage and transport areas, there's large amounts of combustible material. The fiber optic linear heat detection system was installed in a high-tech storage facility with 6 rows of storage racks across 2 buildings. Each rack had 8 levels, and the linear heat detection system provided full coverage of the racks. And what I mean by that is that it was deployed within the rack itself. You can see it going backwards and forwards like this. The reason for this is they wanted to be close to the source of any fires to get a very quick and accurate location. Across the facility, 11 fire lasers were installed. And you can see here where the sensing cable was installed within the rack frame. Here are the 11 systems within the control room. The smart alarms, in this case, configure a maximum temperature of 66 degrees, rate of rise 20 degrees C per minute. The system integrated was using relays to fire control panel and Modbus to SCADA. But in addition, the user also wanted additional visualization. It's quite a complex horizon. They want more intuitive understanding of where the fire was. So they used Bandweaver's MaxView software solution. And this is what it looks like. So this is a screenshot of the MaxView software. Here you can see you have section 1, section 2. In section 1, you have 23 of the shelves. You can see the maximum temperature at the top of each of the shelves. And you can see here that row number 1 has triggered an alarm, and you can see the maximum temperature there. So if you click on row 1, you get the shelf view there. You can see the 8 levels of shelves. You can see it's the lowest shelf which has the alarm, and on the distributed temperature trace, you can see the precise location of that fire. So it allows you to very intuitively exactly pinpoint where that fire is. Moving on to car park protection. This is with our partners SenseTek, who installed this in the Netherlands. It's an indoor car park. These can be dusty environments with exhaust fumes, can be very challenging for smoke detectors. In this case, a redundant loop configuration was installed, 2 loops, one of just over 3 kilometers, one just under 4 kilometers. And the cable was installed with 8-meter spacing between the cables as per the standards in the Netherlands. You can see examples of the cable installed at ceiling levels. You can see it's in multiple environments, facing the outside here, multiple levels, low ceilings. It's very flexible, can be installed across multiple environments. In the Netherlands, all systems must pass a fire pan commissioning test, which involves a half-meter pan of fuel being ignited. The amount of fuel depends on the wind speed within the facility, and the system has to detect this. The ceiling height varies from 2.5 to 3.5 meters typically, and so the different levels of alarms will vary depending on that. Typically in the regions of 7 to 13 degrees C per minute for the rate of rise, and deviation of 10 to 15 degrees C. We'll see a video of one of the system commissioning tests. In this example, the alarm sounded within 25 seconds. It's a 2.4 litre pan test with a wind speed of 1.6 meters per second. So if we look at the test here, you can see SenseTek starting the pan fire, and it gets up to speed. We'll see the wind speed indicator, and then after 25 seconds, you will hear the alarm go off. There's the wind speed indicator. There you can hear the alarm going off. In this case here, we did a measurement for the test, and you can see the temperature profile rising through the duration of the test, which is about 2 to 3 minutes. We detected at 12 degrees C. It was a very cold car park. It was 5 degrees C, so we detected with a 7 degree rate of rise after 25 seconds. But you can see the maximum temperature of this test was 25 degrees C. These tests are mandatory. So a traditional based system will not detect in this kind of test in winter. So increasingly the market is moving towards fiber optic based systems that are much more robust and can pass these more rigorous testing regimes. Moving on to ceiling void in pharmaceutical facility in Singapore. This was done with our partners Innovative Energy in Singapore. This was for Singapore-based pharmaceutical company requiring fire protection for their employee canteen. The local regulations dictate heat detection and continuous measurement was required. They'd already found they had challenges within ceiling void. The dust was causing false alarms, blockages, very difficult to maintain and test getting into these confined areas. Installing multiple powers and network ports, they found it very challenging. So they wanted to go with a single cable installation, a single fiber optic loop run, divided into 6 zones. You can see the cable within the ceiling space here, and you can see the system here connected to the fire control panel. So a very simple installation, but very robust for what the customer wanted here. Moving to a more complex arrangement, Istanbul Airport, again installed with BTS Yankin. Istanbul Airport is one of the largest international airports in the world, capacity of 200 million passengers, 6 terminal buildings. And it's the biggest IT project in Turkish history. It's the world's first airport with a tier 3 classification as a data center. and as a result, it's very complex technical infrastructure, 72 different subsystems within the airport. And you can see this in the fire detection system. There's multiple detectors across the airport, tens of thousands of sensors, and multiple building management systems, fire control panels. So, our system, we didn't know which system we were going to integrate with. We didn't know which, so we had to have a very flexible architecture. We've installed with BTS Yangin 18 systems to date, with more than 43,000 meters of cabling in road hangars, tunnels, hangars, and cable galleries. So we'll look at some of these examples within the airport. So road tunnels, as we said at the beginning, road tunnels is what this technology was originally used for. So it's been in a number of years, fairly simple installation with typically a sensing cable installed in the roof of the tunnel. Cable trays, in this scenario, 4 cable tunnels were protected. These are the power cables going to the cargo buildings, 4 kilometers in total. And it's quite common in industrial facilities for the cables to be monitored in going into the facility using this technology. There's different configurations used. Sometimes, for the larger cables, you might have a single cable per power cable. You might have one across the space. You might have one clipped in the local vicinity of the cables, or you might have one laying on top of it in for example, a serpentine fashion. So it's very many different configurations. The hangars that were measured, in this case 3 hangars were measured, 3 FireLaser systems deployed. We'll look at the maintenance hangar here, which is very large, 65,000 square meters. You can fix 6 planes in there for maintenance. It's big, so multiple fire detection technologies are required within a hangar. One of the aspects of that was the in this hangar, 8,000 meters, so 8 kilometers of fire fiber cable installed at the cable tray level. You can see the configuration here as it is within this hangar, and so massive facility, a big undertaking. And this next video, which Turkish Airways put together, shows the scale of a full-blown test. It's quite the sight to see. So this is the fire test they did for the foam suppression system being detected by the fire detection system within the hangar. As you can see, quite a spot. So finally, I'll just finish up with a few words on Bandweaver, the company. So Bandweaver has been in operation for nearly 20 years now, has vast experience with more than 3,500 systems installed and more than 30,000 kilometers fiber optic sensing installed. There are more than 300 personnel worldwide. Some of the key product lines include distributed temperature sensing, distributed acoustic sensing. For this presentation, we focused on the distributed temperature sensing, but we will have future webinars on the distributed acoustic sensing. In terms of global presence, we have offices across 5 countries. I'm based in our London office and manage the UK-based entity. Regarding international standards, these are obviously critical for fire detection applications. Below are some of the standards we adhere to, some of the bodies we work with in terms of implementing and getting certified. Reliability is also top priority. Bandweaver, something we work very hard on. The FireLaser mean time between failures 29 years. Something we're always monitoring and strive to improve on. We work with some of the global leaders within the fire detection industry. Here are some of the customers and companies we work with on a global basis. We're a trusted supplier, have extensive repeat business, and we're keen to keep extending this customer base. So in conclusion, I'd just like to sum up in a few words. One of the key benefits of the fibre optic linear heat detection is it provides complete coverage at all points of the assets. It's a robust, reliable technology, no moving parts, immune to electromagnetic interference, not susceptible to corrosion, can last more than 30 years. So you get a very low cost of ownership. In terms of performance versus conventional systems, the fibre optic linear heat detection system is excellent. You get rapid detection, lower levels of false alarms. We have the highest performance system available with the Bandweaver system FireLaser, and Bandweaver has extensive experience in fibre optic linear heat detection applications with more than 3,500 installations worldwide. So I just take the opportunity to thank you for your time, open this up for questions, and Mark has been fielding the questions, and hopefully we'll asking them now. Thank you very much.
Yeah, thank you, Richard. Very, very informative. We've got quite a few questions coming. I'm not sure we'll get through all of them today, but for anybody we don't get the chance to answer, you can drop either Richard or myself an email. Our email addresses are there in our Zoom profile, should be up on the screen, or you can go to our website and go to the contact page, and you'll see a form there that you can fill out, and then somebody will get back to you generally the same day, and that's for any questions that we can't answer now. So let's get straight into some of the questions that we've had through today. First one, the most commonly asked question is it possible to share the presentation and recording with us? And it's something Richard covered at the start. We will be sending out a link to everyone that registered for this webinar very shortly, where you can download the link and see the presentation afterwards in your own time. Okay, on to other questions. The first one, how tall is the FireLaser when in a rack?
It's 3U in a rack configuration.
That's a nice easy one to get us started with. Do you have a minimum cable specification for the linear heat detection systems?
No, it can operate using standard fibre optic. So as the fibre optic we use for the FireLaser is 62.5 micron, which refers to the diameter of the core, which means you can get the maximum power in there, which is how we achieve the maximum sensitivity. So as long as it meets telecom grade standards, that's fine. Then you have to have a cable that protects it sufficiently, but also has the thermal lightweight enough so it's easy to install and also react quite quickly thermally. Another factor to take into consideration is the approvals. So the cable needs to also go through the approvals as well. So if the approvals are important, it needs to be the cable that goes with the approvals. If approvals is not a factor and the customer wants to choose their own cable, that's something we can help select with, or they can use ours. We have a very competitive offering on that front.
Thank you. The next question, a two-part question. Are the smart zones a license option or standard? And also with the smart zones, you referred to 1,000. Is that per channel or is that per DTS?
No, good question. So no, it comes as standard, and that's the same with all the software required for the FireLaser to operate. We want this to be a simple transaction. You buy the unit and you have everything you need to go with it there. So it's included there. The 1,000 zones is across the system. It's not per channel. I don't know of any cases where it's even comes close to using all of those, so it hasn't been an issue. If it ever becomes an issue, it may be that can be increased, but at the moment, that's the 1,000 grains is across the system.
Okay, thank you. Next question: what is the maximum length of cable that has been connected to your linear heat detection unit?
So for the linear heat detection, in terms of approved systems, it's 10 kilometers. And we talked about measurement time. You know, when you start going longer than 10 kilometers, you need to start having longer measurement time. So generally for fire detection, that doesn't happen. And certainly for approved systems, it's not longer than that. For other applications, you know, power cable monitoring, pipeline monitoring, you know, we can go 80 kilometers per unit measuring in both directions. So the technology can do that, but for fire detection, 10 kilometers is the limit per channel. So just to be clear there, if you have 4 channels, you can measure up to 40 kilometers, you know, across a number of assets, but the longest distance you can get from the unit is 10 kilometers.
Thank you. Another question. You have mentioned VESDA systems. How is your linear heat detection comparable to it? Could it be considered as a replacement for a VESDA system?
Yes, no, it's a good question. So the VESDA, I believe, is referring to the aspirating smoke systems. They're one of the manufacturers of those systems, and you know, it's a different detection mechanism at the heart. So it's detecting heat as opposed to smoke. So whenever, you know, take into account a design of a system, you know, the user needs to take that into account, because depending on the risks, etc., there's different horses for different courses. But what we do find is that we replace a number of VESDA systems where, you know, when we look to those environments, there's dust or particulates in the air, high humidity that just block or cause false alarms for those systems. So that's one area where we see that we replace VESDA ones. The others are, you know, the cost. Once you start getting into larger facilities, the economic benefits move much more towards the fire optic in linear heat detection systems. So again, it moves towards that. But in some cases, for certain facilities, customers will go with the smoke aspirating. Sometimes they'll use both of them in the same facility. So it's, you know, it really depends on the fire strategy. But yes, we have replaced a number of aspirating smoke systems.
Okay, thank you. And on to the next question. What's the maximum number of channels available? You referred to FireLaser with 4. Do you do any other unit?
We don't today. We do 4 for the fire detection. Again, for other applications, we go higher than this. But because in the example there, we showed that, you know, this technology, you're switching from one fiber to another, so you only have one channel active. So if you go to more than one channel and you want rate of rise, it makes it quite difficult. So 4 is the maximum number of channels for the foreseeable future.
Okay, on to the next one. And you have CCTV cameras integrated into a linear heat detection system.
Yes, you can. We have with using the MaxView software. So the DTS units are completely self-contained. So once they're up and running, they don't need any PCs plugged in or anything. They're running, but they can export to using Modbus. So you get the location there. So using building management software, you have the locations. You can use the CCTV in the building management software or the SCADA, or the MaxView software by Bandweaver has the facility to integrate multiple different inputs. So, you know, CCTV, alarm sounders, environmental sensors, and there's some fairly large projects we've done on large utility tunnels where, you know, they're fully automated, and MaxView's at the heart of that, with multiple technologies, including DTS and CCTV, amongst many others.
Thank you. Here's a good question. Can you detect multiple fires simultaneously?
Yeah, it's a very good question, and yes, yeah, there's no limit to that. Yeah, it's detecting all along the length simultaneously within that. So yes, absolutely, you can.
Okay, on to the next one. Which software is provided with your DTS units, and can you do either include or separate visualization software?
Yes, yeah, very good questions. So the as standards, the DTS configuration manager software is included, and so when you're configuring it, you plug in a laptop, a PC, and you can configure it using that. You can do it using the touch screen as well, but it's very slightly user friendly using a larger PC with the keyboard, and that's included. So when you're plugged into the system, you can look at the history of the data, you can save data onto the PC. For most fire detections, people don't do that. And also the Modbus is, you have a Modbus map, so it's very simple. It automatically exports the Modbus. So everything you need to do is very simple. But some people do use the DTS configuration manager for visualization, because you can plug it in to a central hub, and you can then plug it into 10 DTSs, and you can view the temperature traces across those 10 DTSs up to 40 channels. You can see that. So some people do that. It's still not that intuitive in terms of the actual asset in the installation. So the next level of intuitive visualization is the max view, where you can see you can have a map, you can have an asset view. We showed the example of the warehouse in there, where you saw it, the different shelves and in there. But this can be whatever the user wants. So they can have photos, they have site maps. It's user configurable, and that's very powerful. That's not included. That's an added product that we have some standard packages, or we work with the customer to have a very detailed customized view of that.
Okay, thank you. We're running almost out of time. There's just one or two very quick questions. Should the fiber optic cable be damaged, how long is the detection time before the system is aware the cable's been damaged, and how good is the accuracy to the fiber break location? Right,
no, very good questions. So it would detect on that measurement cycle. So if you have a measurement cycle and the fibers either broken before that or on that measurement cycle, it knows straight away. So you get a specific fiber break alarm, and then it only measures up to the point of the break after that. So it shouldn't you won't get fire alarm, you'll get a fiber break alarm, and it's instantaneous and it cuts off everything else. So you can still carry on measuring. In terms of the accuracy, it depends a little bit on the nature of the break, but generally 1 to 3 meters of information you may lose around the break, depending on how what the reflection is like at the end of the break. So sort of minimal loss, so 1 to 3 meters.
Okay, thank you. And for warehouses, if a project doesn't have racks, do you have an option for wall-mounted cable as well?
Yes, I mean our installers would be the ones to really get the details, because they've probably done multiples of that. But yes, wall and ceiling mounted are possible. Ceiling mounted is the most common. I've seen some on wall mounted in specific applications. So absolutely yes.
Okay, I've got an important one. Do you serve a global customer base? And also, what is the route to market? How can I buy your products?
Right, very good question. Yes, we absolutely do. First touch is get in contact with us. As Mark said, you have our email addresses in there, or the contact us page on the website, and then we will get in contact and work out what the best arrangement is. So in some of these examples, we talked about some of our local partners, BTS Yangin in Turkey, Innovative Energy in Netherlands, Innovative Energy in Singapore, SenseTek in Netherlands, and we would more than likely put you in touch with a local partner that has the local expertise in design of system, installation of system, and ongoing maintenance and support, and so they're really the best people to deal with in most cases. there's some areas we don't necessarily have representation, in which case, we're open to deal direct with us, or if you're interested in being a representative in that area, also please get in touch.
Okay, I think we're out of time. There's just a final question to wrap it up. There was a question really up with the FireLasers. Do you do a wall-mounted option for the fire as opposed to rack?
Yes. So in multiple cases, this is there's wall-mounted solutions for this. So in fact, you saw on there's one in here. There you can see it wall mounted there, and in the Singapore system, a wall mounted system there. So yeah, there's different options for the wall mounted system.
Okay, so I think we only got through about a third of the questions, but unfortunately we're out of time, so I'll just hand back to Richard to finish up.
Well, thank you very much, Mark, and apologies if we didn't get to your questions. Please drop us a line afterwards, and we'll try our best to get back. As Mark said, there will be links to the presentation, the video. This has been recorded, so if you want to watch it again or share it with anyone else, both options are possible. So you have my details there on this slide. So please do get in contact, and I'd just like to say thank you very much for your time, taking the effort to take part in our webinar. It's very much appreciated. If there's any topics for future webinars you want to have in addition to this, we'd be very happy to incorporate that. So please do let us know. Thank you very much. Good evening, good morning, good wherever you are in the world, and have a great day. Thank you. Bye.